star formation and their death. Okay, I think so. We should start with the presentation. So, hello everyone. My name is Aryan. I'm 13 years old. I was born in Bihar, but I'm living in Ludhiana for my education purpose. And for today, our topic would be about early stars. Introduction to star formation. Stars are formed from the collapse of gas and dust in space. The process begins shortly after the Big Bang, leading to the creation of the first stars. Understanding star formation helps us learn about the origins of galaxies and the universe. The Big Bang and the early universe. The Big Bang occurred approximately 13.8 billion years ago, creating the universe. Immediately after, the universe was filled with hot and dense particles. As the universe expanded and cooled, conditions became suitable for star formation. So, so the Big Bang occurred approximately 13.8 billion years ago, which created the universe. And after that, what happened? That the universe was filled with very hot and dense particles. So after that, when the universe started cooling, and then when there was conditions suitable for star formations, the first stars were formed. And these there's an hy- uh, there's a guess in the scientific community that the first stars could have been the population 3 stars, which we would discuss later in the presentation. So, formation of the first gas clouds. Hydrogen and helium gas began to coalesce into larger clouds called molecular clouds. These clouds are the birthplace of stars containing the raw materials needed. Gravity causes these clouds to contract and become denser over time. So, Saksham, I have a question for you. So, my question is that whenever there are these gas clouds, and whenever they start contracting, there's an upper limit to this star formations, this star's mass, and if it gets too much mass, it just repels it away. So, do you know that? So, do you think that this upper limit can be challenged for very large stars? Hello, Saksham.
Could you repeat your question?
So, my question is that when these gas clouds start contracting and become a star, there's a limit to the star, and if it gets near to that limit, it will repel that extra gas away. So, in the early one, and my question is there any exception to this? Do you think that there can be an exception to this upper limit? What do you think? Yes. Okay, so like we can put it this way that is there any way that we can bypass this star's mass limit? Did you get my question? Saksham and Satyajit, do you have any guesses?
No.
Okay, so Saksham, do you have any guesses? Okay, so let me answer it. People suspect like this is an hypothetical type of star. These are called quasi stars, and they could be like tens of millions of times more massive than a sun. And the way they form, I think so. Saksham, you have joined earlier classes, So you should know this one, that because there in the early universe there could have been dark matter halos, places where the dark matter concentration was way more and it attracted gas and dust, and that could have made quasi stars which were very large stars, and they attracted so much mass like that upper limit was not of any use because of this dark matter. It's attracting more and more gas. So what could happen that they could have a black hole in has their core because the star is so massive, and this is the so these types of stars are called quasi stars, and these stars could explain the very large supermassive black holes that we see. So this is an exception for this upper limit of stars. So let's get to the topic, gravitational collapse in star formation. Whenever a part of a molecular cloud begins to reach a critical density, it begins to collapse under gravity. This collapse increases the temperature and pressure at the core of the cloud. This process eventually leads to the formation of a protostar. So now we will talk about star formation, these protostars and T-Tauri stars. So uh, the reason these neutron stars spin very fast is that they were first molecular clouds, and as we know that if a big thing is spinning and it contracts, like if a skater is spinning and if he contracts his hand, what would happen, that he would spin faster. So this is the reason stars and neutron stars spin very fast. That is because the molecular cloud that they were born with was already spinning. The protostar phase overview. A protostar is a young star still in the process of formation. It is surrounded by a cocoon of gas and dust that it is excreting in form. During this phase, the star is not yet hot enough to initiate nuclear fusion. So what happens when the gas cloud starts to rotate? The becomes a star, and that star is called a protostar. This is a very young star which is still in the process of formation. It is surrounded by gas and dust that is accelerating into it. So at this point, the star is not hot enough to initiate nuclear fusion. That happens when it reaches the main sequence star's status. Protostars details as the core gas collapses, gravitational energy converts into heat, raising the temperature. When the core temperature reaches about 10 million Kelvin, nuclear fusion begins. The protostar then becomes a main sequence stars once fusion is sustained. As you can see in the picture, it shows the protostar formation. It What happens is that the gas starts collapsing onto itself, and the gravitational energy converts uh, this gas into heat, raising the temperature. As we see in the case of a black hole, it has an equation this where matter and dust are accelerated to very near speed of light. So that is also the case with protostars. What happens is that uh, there's a ring around the protostar of gas, and it starts accelerating due to gravitational energy, and it converts it into heat, which raises the temperature more and more. And when the core temperature reaches 10 million degrees, 10 million Kelvin, nuclear fusion starts to happen. Types of protostars. Class 0. So, class 0 protostars are the earliest stages, deeply embedded in their natural natal cloud. They are categorized by high infall rates and strong submillimeter emissions. These protostars are often not visible in optical wavelength due to dust obscuration. So what happens is that the signals that we reach, the radiation that we're getting from these class zero protostars, it's not very visible uh, because the core temperature, the temperature is still not high enough for UV rays or gamma rays. But what happens is that it also has a cloud of gas and dust surrounding it. So these types of stars uh, are not often visible in this wavelength, optical wavelength. They are still deeply in their natural clouds. Types of protostars class 1. Class 1 protostars are more evolved with less surrounding material than class 0. They still excrete material but at a slower rate and often show infrared excess. They typically have outflows and jets as part of their formation process. So they also excrete material but at a slower rate, and they now begin to give infrared wavelength. So as you can see in the picture, there's a nebula, the cloud of gas and dust. It becomes a protostar, then becomes a main sequence, and then becomes a red giant, and the death of the star happens. So, ladies and gentlemen, any questions by anyone? Saksham and Satyajit, do you have any questions? Okay, I think so. There's one question. It's about what is a submillimeter emission. Okay, I think so. We should talk about that at the end of the presentation. We'll take this question at the end. So, I think so. There are no questions right now. So, we'll begin with the presentation now. Types of protostars, class 2. So, these are young stars with prominent proplanetary disks. The surrounding envelope of dust and gas has mostly dispersed. They are often visible in optical wavelengths and are called T Tauri stars now. So, N protostar of class 3 is also called an T Tauri star. They are now visible in optical wavelength, and the uh, dust and gas that had surrounded it is now very dispersed, and these are very young stars. Types of protostars class 3. So class 3 protostars have very little circumstellar material remaining. They are approaching the main sequence phase with weak or no emission lines. These stars are often called weak line T Tauri stars. So this is the last stage of being a protostar. They are approaching their main sequence star phase where they can begin nuclear fusion, and these stars are often called weak line Pleitori stars. They have very little gas and dust surrounding them now. Now we will begin with the next topic, which is called T-Tauri star. So T-Tauri star is a young star. These are stars under 10 million years old, and they are in their final stage uh, of pre-main sequence stage. They are lacking core nuclear fusion. It generates energy strictly through gravitational contraction. It is categorized by violent stellar winds, extreme brightness fluctuations, and dense planetary disks. These visible infants actively form planets before entering adulthood. So our star sun was also an T-Tauri star at some point, and its remaining dust and gas formed the planets that we see: the Jupiter, Saturn, Mercury. and they are categorized by very strong and stellar winds. They also face extreme brightness fluctuations because there is gas and dust surrounding it. So they also have very dense planetary disks. So they still have dust and gas surrounding them, which is in a disk-like shape, just like the accretion disk, which also generates heat and light. And these Titori stars are just entering their pre-main sequence stage. Main sequence star formation. Once nuclear fusion begins, the star enters the main sequence phase. Main sequence phase, the star stabilizes, has its balances gravitational collapse with outward pressure. The duration on the main sequence depend on the star's mass. So as we have said that the duration of the main sequence star's phase depends on the star mass. What we mean is that how fast it uses this his mass. So the case is that very massive stars have very little life cycles, and there's also an equation for this. uh, I only remember the luminosity part. It is luminosity is equals to uh, mass raised to the power of 3.5. So, and star twice the mass would be about 10 times bright. So, we can just imagine that with just doubling the mass, it becomes 10 times more luminous. And the star stabilizes as it balances gravitational collapse with outward pressure. So, that pressure is provided with nuclear fusion. And once this stage begins, the star now balances the gravitational collapse with this nuclear fusion energy. So, ladies and gentlemen, any questions? Saksham and Satyajit, do you have any questions? Hello, Saksham and Satyajit, do you have any questions regarding the topic?
Yeah, it's good.
Okay. The role of mass in star formation. The inertial mass of this molecular cloud determines the star's eventual size and type. Massive clouds, massive clouds tend to form more massive stars which have shorter lifespan. Low mass clouds produce smaller and long lived stars like our sun. So, this role of mass in star formation. So, I've also mentioned the quasi stars. So, these were hypothetical stars that could have lived uh, around uh, millions of years ago when dark matter halos attracted a lot of mass, and some people suspect that these stars could have had black holes at their centers, and their mass could have been comparable to dwarf galaxies. So this is the role of mass in star formation. It determines the star's luminosity, and it also decides the star's lifespan. Factors affecting star formation efficiency. Turbulence within molecular clouds can inhibit uh, or promote collapse. Magnetic fields can slow down or channel the collapse process. External forces like supernova shocks can trigger star formation. So I have a question for everyone. Is there any way, like, is there any factor that contributes to the star's lifespan? uh, except like I'm talking about factors affecting the star's lifetime, but I do not include the mass and other things, like the things in its core. Is there anything in the core or in the star that can affect its lifespan? Okay, so do we have any guesses, Saksham and Satyajit?
Aryan means you asking that how does the size of the star expand with its life? Am I
No,
right?
I'm asking that is there anything in the star that can affect its lifespan? Do you,
I think
Satya-
Aryan, it's when the star completes its fusion of hydrogen and helium, then it will affect its lifespan because after that the star will expand and then collapse in it, depending on its mass.
okay, so like the materials in its cores, like carbon, oxygen, do these play a role in the star's lifespan?
Yes, you can see that when the star is using hydrogen and helium, it is normal and main sequence star. But when this fusion gets disturbed due to the mass of the star, then this fusion of hydrogen and helium no longer remains. If the star is main sequence star like our sun, then it will expand and contract to the small body size of the Earth, forming a white dwarf, and that white dwarf will fuse carbon and oxygen.
Okay, so Satyajit, do you have any opinion on this?
So I have four guesses. So first of all, is how hot its core is. That is,
Okay,
hotter the cook, the fuel burns faster, and hence the shorter the life is.
okay,
So that is the first one. The second one should be how much fuel is available, the hydrogen basically, and like more fuel equals longer life.
yes. Okay,
And the third, yeah, these two are the major ones in my mind, right?
okay, so like my question was not about the mass and the stuff. I was talking about the materials that are in this star, that how can they affect the star's lifetime?
So the composition,
Yes.
um, I'm sure they would be different because the low metallicity was very common in the earlier universe, but I'm not sure how they affect the lifetime.
Okay, so have you heard about metallicity?
Yeah,
So do you know what is that?
basically it's a term that astronomers use for anything that is heavier than a helium, basically, and it doesn't typically mean metal in our typical chemist terms. So astronomers basically call everything that is heavier than a helium as a metal.
So uh, what do you think that does this metallicity have an effect on this star's lifetime?
I'm sure it does affect it, but I don't actually know in which sense. Like it does contribute to a longer life or a shorter. That is what I'm not aware of. But it must be different because earlier universe had this low metallicity very common. So all the
Okay,
stars at those time will be of low metallicity.
okay, so Saksham, what do you have to say on this metallicity? Can this metallicity affect the star's lifetime? Hello, Saksham.
Yes, Aryan.
What do you think that does metallicity have a role on the star's lifespan?
Yes, Aryan, and I also agree with the thoughts of Satyajit.
Okay, so you are right that yes, this metallicity has a pretty big effect on the star's lifetime. So as Satyajit mentioned, metallicity, uh, it metals that any element heavier than helium or hydrogen is called a metal, and how it affects the star's lifetime is pretty interesting. Like more metals, heavier metals, what happens that these photons have a very hard time escaping. So in the center, it gets released, the photon gets released, and there are very hard metals. The metallicity is high, and what happens is that it bounces around a lot, which uh, which help in the star for expanding, and it turns slightly cooler. Okay, so this is how metallicity has an effect on the star's lifespan, and for high mass stars, uh, they blow off mass very faster, and which shortens their lifespan. Okay, so do you have any questions? And
Aryan, do you know about star eruption?
okay, what's that? I think I don't have any idea about that. Star explosion or what did you say? I couldn't get it.
Do you know about star eruption?
No, Saksham, I don't know.
It happened in the Eta Carinae system.
Okay, so what's that? A star eruption?
In this, what happens that the that in the binary star system, the st- if there are two stars in the binary star system, let's suppose that the first star is about 90 solar masses, and the second star is about, you can say, 60 solar masses. Then this and if both stars are nearing the end of their life, then before the supernova, they will do do an event which is known as great eruption. It is what happens that the both stars will lose the huge amount of solar masses. This will make them very unstable and will force them to do a supernova explosion.
Okay, I'll
Th- This happened in Eta Carinae supernova.
okay, I'll see about that. Okay.
Okay, Ari.
So, metallicity. In astronomy, metallicity measures the proportion of a celestial object's mass made of metals heavier than hydrogen and helium. Because these metals are forged in stars and are scattered by supernova, younger stars have have higher metallicity than older stars. This trait acts as a cosmic timeline and determines a system's likelihood of forming rocky planets. So, Satyajit and Saksham, do you know why these younger stars have higher metallicity?
Can you please repeat your question?
Why do younger stars have higher metallicity?
Simply because older stars had fewer metals available when they were born, right? Because right after the Big Bang, the universe majorly contained nothing but hydrogen and helium, and that was it.
Yeah.
So there was almost no carbon, no oxygen, no iron.
Yeah.
So the first generation of stars formed from nearly pure hydrogen and helium. So that's why it were of very low metallicity. So thereafter, those stars died, and inside those stars,
Yeah.
fusion created heavier elements like carbon, oxygen, silicon, and what else? We have iron. And when they exploded and shredded materials, these elements were released into space, and the gas between stars become richer in metals. And
Yes.
thereafter, new stars formed, and they were of higher metallicity because they had more carbon, more oxygen, and more air, and stuffs like that.
So you're right, because these older stars had lower metallicity. They formed higher metals. They died by supernova, and that supernova gave mass for younger stars to form, which in turn made these younger stars have higher metallicity. The life cycles of stars. So stars go through various stages and form protostars to main sequence and eventually to death. Massive stars end as supernovae, while smaller stars like the sun becomes white dwarf. The material from dying stars can be recycled into new star formation. So I have a question for you, everyone, that why does a star explode? If like we are seeing that the star just ran out of its material, then it should just implode. It has nothing that could help it to explode. It should just implode. So why is that, Saksham and Satyajit?
Means you are asking that why does a supernova explosion occurs, right?
Okay, no, that's not the case. I'm asking why should a star explode at all? It basic sense like it should implode. It has ran out of its material that for nuclear fusion it should implode in itself. So why does that explode?
Aryan, can you explain your question with an examples because I'm not getting with you.
Okay, so in the case for a black hole, what happens? Let's assume there's a star. It has exhausted all of its fuel and it's pretty massive. What would happen that gravity will win and this star would get collapsed into into a very small point, and that is called a black hole. But for other things, what happens is that they shed their outer layers and supernova happens. The outer layers of gases and other things are blown away. So why does that happen? Okay, Satyajit, do you have any guess?
Aryan, this happens due to the imbalance of gravitational and radiation pressure.
Okay, so that does not answer the question why should it explode. So Satyajit, do you have any guess?
My guess would be the star first collapse inwards and then like maybe like a rebound or something. I am not sure.
Okay, so let me answer this question.
But the first step indeed should be the inward collapse. So because that
Yes.
is the logical sense.
So what happens is that for the case of white dwarfs and neutron stars, what happens is that it first implodes and the core it gets collapsed. It forms an white dwarf or a neutron star, and that stops that implosion because of this poly exclusion and stuff. And there's one more thing, like poly exclusion could not is not the only contender for this explosions thing. It is also neutrinos. So yep, they there are like trillions of neutrinos are then created and they expand outwards. We know that they do not collide with materials much, but if there are trillions and trillions and there is trillions of neutrinos, they will collide with a material. The chances are still low, but it will happen. And so I think so. We have discussed this in our previous presentations when we talked about W and Z bosons, how they interact with the neutrinos. So neutrinos uh, interact with Z bosons. So that is how neutrinos help the star to explode. So did you get me, Saksham and Satyajit?
Yes, I do.
Okay. Star formation in galaxies. Star formation occurs in specific regions called stellar nurseries within galaxies. Spiral arms of galaxies are rich in molecular clouds and active star formation. External factors like galaxy collisions can enhance stars formation rates. So this galaxy collision thing, so we know that the Milky Way is going to collapse with the Andromeda, and that will result in very high star formation rates because there is going to be a lot of gas and dust colliding with each other. So there are specific regions in space called stellar nurseries, which are very rich in gas and dust. And these spiral arms of galaxies are also rich in molecular clouds, and they're actively doing star formation. Lifespan of a star. So in our very previous presentations, I don't. We have talked about this equation. It's the main sequence lifetime formula. It calculates a star's lifetime based on its mass, derived from the mass luminosity relation. It shows that higher mass creates greater core pressure, making stars burn exponentially faster. Consecutively, massive stars live only millions of years, while low mass stars endure for trillions. So, Satyajit, have you heard about stellar flux? Like, it's
No, I haven't.
do you have you seen that symbol? Like, it's at raised to the power of 4. Have you heard about that?
No, I don't have any idea.
So it's the radiation flux. So the luminosity, what could it be? It would be the energy radiated per meter square of the star. So it could be, the star is also in sphere. So it could be luminosity is equals to 4 pi r square times at raised to the power of 4. Or we can just say that luminosity is area times the radiated flux. And if we just can uh, in simple terms, what the case is that L is equals to m raised to the power of 3.5. And those in the picture we see that there is an uh, symbol near L. It is the luminosity of sun and the mass of sun. So there is also a symbol for the earth too. So Satyajit and Saksham, did you get this formula? Hello, Saksham and Satyajit. Did you understand this formula?
Yeah, kind of.
So, do you have any questions about this? Okay, I don't think so. Death of a star. A star's death depends entirely on its mass. Low mass stars like a sun expand into red giants, shed their outer layers as planetary nebulae, and leave behind cooling white dwarfs. Massive stars explode violently in supernovas, leaving behind incredibly dense neutron stars or collapsing completely into inescapable black holes. Supernova. So it's the colossal expansion of a dying massive star. It occurs when a star collapses under its own gravity after running out of nuclear fuel. These brief blinding blasts forge heavy cosmic elements and outshine entire galaxies before leaving behind incredibly dense remnants like neutron stars or black holes. So now we will talk about the types of supernovas too. So, and supernova happens when the star runs out of nuclear fuel, and this is a massive source of heavy elements. So, Saksham, you have raised your hand.
Yes, Aryan. Can you explain me that how many types of supernova explosions are there what what happens in each type?
Okay, so that is exactly the thing that we are going to uh, learn in this presentation. So, type 1A supernova. So, we are just going to talk about them. So these do not involve massive star collapse. Instead, a white dwarf in a binary system pulls in too much matter from a companion star, triggering a catastrophic thermal nuclear explosion. They are famous for their uniform brightness, making them crucial cosmic tools for measuring astronomical distances. So, okay, type 1 supernova, what happens is that there's an binary system, and that white dwarf, there's a white dwarf. There is have an upper limit uh, of their mass, which is 1.44. It is called the Chandrasekhar limit. After that, they will do supernova and collapse. And what happens in this binary system is that it pulls too much matter from the companion star, triggering a supernova. So this includes white dwarfs. Type 1b supernova. These are core collapse explosions of massive stars, typically 25 plus solar masses. They lack hydrogen because the star sheds its outer layers via strong stellar winds before exploding, but they still show strong helium signs. So these are core collapses of very massive stars, which are about 25 plus solar masses. They lack hydrogen because the star sheds its outer hydrogen layer via strong nuclear winds before exploding, but they still have helium signs. Type 1c supernovas. So these are core collapse explosions of massive stars, but they have been stripped away from both of the outer hydrogen and helium layers before exploding, leaving a spectrum that lacks both of the elements. So they have already used their helium and hydrogen reserves. So that is why there are no signs of hydrogen and helium in them. Stellar remnants. A white dwarf is the extremely dense, Earth-sized core left behind after a low-mass star like our Sun dies, lacking nuclear fuel. It shines purely from leftover heat and slowly cools over trillions of years. It resists gravitational collapse using electron degeneracy pressure, capping its maximum mass at 1.44 solar masses. So, Saksham and Satyajit, I have a question for you. Why are there no electron and proton stars? Hello, Saksham and Satyajit. Hello, Saksham and Satyajit. My question is that why are there no electron and proton stars?
I don't really know.
Okay, so
I
like
think Aryan, that's because electron and proton is unable to fuse.
okay, unable to fuse. Like, what do you mean by that? Unable to fuse? I didn't get that.
Means red star can fuse electron and proton.
Okay, with electron and protons. Okay, so you know white dwarfs, right? These are the closest thing to electron stars. Uh, and what do we mean by that? Is that when this star collapses, it forms like the atoms get they get stripped of their electrons. They get stripped of their electrons, and there is one thing in quantum mechanics called quantum spacing. If you have heard about that, it is the minimum distance that two electrons can have. There's quantum spacing and they interact via their quantum spacing. This is also because of the Pauli exclusion principle, like two electrons cannot occupy the same place, and that is what we call the electron degeneracy pressure. So if that's the case for white dwarfs, so why are there no proton stars? Like if white dwarfs are the closest thing to an electron star, why are there no proton stars? Satyajit and Saksham, do you have any guess? What Satyajit, you want to say something?
So is it like the electrons and protons basically are forced to make up neutrons in normal case? That's why the electrons and proton star doesn't exist. And again, the closest thing is white dwarfs because the gravity is just not so strong enough so that they can squeeze and form neutrons.
So the thing that you said that they form neutrons, these two form neutrons is correct, But the case with white dwarfs is that they get ripped of their electrons, and these are the closest things for electron stars. But like, if we keep that aside, that neutron thing, they form neutrons. So can that, if we just do not see that neutron star, neutron formation part, can there be an proton star if we just overlook this thing, the neutron formation? So did you get my question?
Uh, does that mean that we are making the protons exist independently and not
Yes.
along with the electrons?
Yes. Can that be the case?
Again, like charges repel each other, right?
Okay, so but that's the case with the electron degeneracy pressure too. Electrons repel each other. They are negative charges. So these are the same charges. They repel each other, but still there's an white dwarf. So can that be the case for this proton star?
Why is it the case for the white dwarfs at the first place? Let's just talk about electrons.
Okay, they get stripped of their electrons, and like,
What does it mean? I didn't quite get the phrase.
okay, so I I don't think so. I can explain that good about those electrons. These electrons follow the Pauli exclusion principle, and they are not they are not crashing into each other, and that is how an white dwarf is stable. So they are like this. They are just resisting the gravitational collapse by this Pauli exclusion principle.
But white dwarf is extremely dense, right?
Yes.
And yet they are somehow stable, even being the same charged particles.
Yes.
Okay.
So
And then you asked if this could be the case for protons.
yes.
I would deny for the same reason I didn't for electrons, but again, there is an exception lies as we see in the case of white dwarfs. But I don't think there is one for protons, though I'm not sure.
Okay, so why do you think that it should not be the case with protons? If
Well, the same reason I thought it shouldn't be possible with electrons, but then you said you gave the reason for some exclusion principle, I guess,
yes,
which I
they
don't
can.
quite understand. But uh, the same reasoning I gave for electrons, why they shouldn't exist in this state, is the same I would be giving for protons as well. That is basically the same charged particles and also being dense.
Okay, so the Pauli exclusion principle, to understand that, let's look at neutron stars. They are made up of neutrons. They do not have any charge.
Right.
So, but what's the case with Pauli exclusion principle is that it says two particles cannot occupy the same space. So that is the Pauli exclusion principle, and that helps that neutron stars to be stable and not collapse into a black hole. This is also the case for white dwarfs. It is called electron degeneracy pressure, and in neutrons, it's called neutron degeneracy pressure. So, did you get me? It
So
all,
basically, you just said that one place cannot be occupied by two individual particles at the same time.
yes.
So how does that make sense when explaining the stability of white dwarfs?
Okay. So let me tell you that if you push something into a very small space,
Okay.
it gets more harder to push. And in the case of these neutron stars, this is the same thing. The gravity tries to push in, but the particles in it, uh, by this Pauli exclusion, they are like resisting that gravitational collapse.
Yeah, but it completely depends upon the mass of the thing, right? Because
Yes,
in smaller stars we see this formation of neutron stars, and if we increase the mass by a significant amount, then eventually the gravity wins, and we get a black hole.
yes,
So that is not what I was asking, because in the neutron star there is basically neutrons everywhere, which is not quite like charges. I mean, not in the sense charge, because neutron is basically neutral. But we
yes,
are talking about white dwarfs where we have equal charges that are supposed to repel each other.
yes. That okay. That is also they are trying to repel each other, but the gravity is trying to uh, make a black hole, right? So it's resisting that gravitational collapse.
Okay, but okay, you're talking about gravitational collapse.
Yes,
Okay, so you're saying basically that the gravitational force, that is the force acting inwards, and the resisting force among each particle are perfectly balanced out so that the entire star is stable.
yes,
But the thing is, the gravitational force is always acting towards the inner core, whereas the repulsive thing in between the particles are not quite frankly always outside, because it is the individual force between just two independent particles. It isn't like it's going inwards or outwards, so how is it supposed to cancel a force that is acting always inside?
okay. So whenever the electron repels another electron, what happens is that I don't like how will I
Yeah,
explain.
the repulsion basically says the distance between those two particles would be increasing, that's it.
But that does not happen. The gravity is still exerting at a very high pressure, so still it's
Okay,
still
okay.
stable because
One
of
way
that.
to visualize is basically think of it like the two particles are basically at the same level. It's not like up and down, but it's side and side. So gravity is always pushing both of the particles towards down.
Yes.
Can you visualize it? I mean, the two particles are just side by side. It's not up
Yeah.
and down.
Okay.
So the repulsive force in between the particles is supposed to increase the distance between them, and the gravity is supposed to push both of them down simultaneously. So it's not like the gravity is getting cancelled by the repulsion. That might be the case if we are imagining both the particles up and down. But what if in the case of side by side repulsion?
Okay. So you are saying that these are two electrons, and it's the core of that white dwarf. And if this one pushes it away, what would happen is that gravity will be there, and it will again pull it to its original place. So it's still working there side by
Oh,
side.
how is gravity supposed to pull them to the original place? Gravity
Yes,
always acts inwards, right?
yes.
It's not
It's still
like
acting
preserving.
inwards. It's still
What?
acting inwards.
Yeah,
That the particle is still getting attracted to the core.
yeah, but how is the distance, the original distance, supposed to preserve the original form?
Yes. Okay.
If the resistive force is taking both of it outwards, not
Okay.
in the sense of outwards of the star, but the distance in between those two particles, the
It's
gravity is just pulling it down towards the core, right?
yes.
And those particles are in the same horizontal plane. That's what I'm saying. So how is gravity affecting the distance between both of them, how whatsoever?
So this is the topic of quantum spacing. It's an quantum mechanical. It's in quantum physics that this is the minimum distance that these particles can have. So they are at quantum spacing, and like the gravity is very intense, and these that's why it's very dense. So that's why it goes back to its original position. It's getting attracted to the core, and that is how it's getting that is how it's getting stable.
Okay.
Okay, so Why it's not the case with the proton stars? Do you know?
No, I don't have any idea.
Okay, there's I can't recall the name, but there's an it's another quantum physical thing. Uh, I can't remember its name, but it says that bigger particles like the protons do not generate enough degeneracy pressure, uh, degeneracy pressure to be stable. So that's one of the reason, and yep, that's why it's in quantum mechanics that bigger particles do not generate enough degeneracy pressure. Okay, let's talk about neutron stars. So it's the ultra dense collapsed core left behind after a massive star explodes in a supernova, compressing the mass of nearly two suns into a city sized sphere. They're composed almost entirely of neutrons held stable by neutron degeneracy pressure. They often rotate rapidly, emitting intense beams of radiation as pulsars. So as you talked about these neutron stars, what happens is that the stars does a supernova and the electrons and the protons collide to form neutrons. So that is how a neutron star is formed. Now, black holes. Black hole is the ultimate stellar remnant formed when the most massive stars collapse completely under their own gravity. They pack immense mass into an infinitely dense point called a singularity. This creates a gravitational pull so intense that nothing, not even light, can escape its boundary, the event horizon. Death of stellar remnants. The ultimate fate of a white dwarf is to slowly radiate all its remaining heat into space. Over trillions of years, a duration longer than the current age of the universe, it cools completely to become a dark, inert lump of carbon and oxygen known as black dwarfs, neutron stars. The ultimate fate of a neutron star is to slowly lose its rotational energy, heat, and magnetic field over trillions of years. It eventually fades into a cold, dark, and completely silent sphere of dead nuclear matter, frozen in places, unless it collides with another object or undergoes theoretical proton decay. Black holes. The ultimate fate of a black hole is complete evaporation through Hawking radiation over unimaginable timescales. The quantum effects at the event horizon cause the black hole to slowly leak particles and lose mass. This process accelerates over time, culminating in a violent high energy explosion as the black hole vanishes entirely. So, ladies and gentlemen, any questions? Hello, Sakshan and Satyajit, do you have any questions?
No, we are good.
Okay. So, for the case of a black hole, the death of a black hole. So, Satyajit, have you heard about entropy? What's entropy? Hello, Satyajit.
Yeah. What did you say?
Have you heard about entropy?
Entropy. Yeah,
Yes.
it's basically how organized or not organized things are.
Yes. So, this is my thoughts regarding it of about a black hole. So in a black hole what happens is that material gets squashed into a very tiny space called the singularity, and it means that the entropy of that place singularity is not increasing. So to compensate for that, it radiates the Hawking radiation, the particles, and as time moves on, what happens, this quantum radiation gets stronger and stronger because a lot of more time has passed. So this is my opinion on this black hole and more Hawking radiation. So people say that the uh, like with time the Hawking radiation gets stronger, but I did not understand that. But this is my opinion about regarding it. So what do you think about it, Satyajit? That the about the entropy and stuff.
Let me think about it.
Okay, so Saksham, what do you think about this entropy and that black hole? Hello, Saksham.
Aryan, I think about the black hole as a very massive object where from which nothing can escape, including light. It would be very massive, ultimately billions or trillions of times more massive than the sun, and would be incredibly large.
Okay, so my I was talking about the entropy and the black hole. So in the black hole, what happens that materials get squashed into the singularity. It means the entropy of that system is not increasing. So to compensate for that, it releases Hawking radiation, and with time, the Hawking radiation gets stronger and stronger because the entropy of that system is not increasing. So uh, that is my thinking, my opinion on this Hawking radiation and stuff. So what do you think about it? Hello, Saksham. Did you get me? What was I saying?
No, Aryan.
So do you know about entropy? What's entropy?
No, Aryan.
Okay.
I've heard about it, but I don't know.
Okay. So when like in a cup of coffee, what happens that the particles are moving and moving. So if I pour something like in a glass of milk, if I pour coffee in it, what would happen? That it will after some time, you will see that we will see it mix into the whole. The particles are moving, and that is a direct evidence of entropy increase. So the laws of thermodynamics say that entropy should always increase. And if we go for the case of that, black holes in their core, what happens? There is the singularity. It does not increase uh, the entropy because it's squashed into a very small place. So to compensate for that, it releases Hawking radiation, and with time, the Hawking radiation gets stronger and stronger because more time has passed, and the entropy of that system hadn't increased for a long time. So that is my thinking on it. That is my opinion. So what do you think about that uh, entropy and this black hole lifespan?
Basically, Aryan, I think as same as you're thinking.
Okay,
And I also think that if the entropy reaches the maximum value, the energy will be evenly distributed.
okay. So you agree with me, but I know there are few loopholes into this. So I was just trying to solve them. So Satyajit, what do you think?
I was going through an imagination.
Okay.
Suppose two black holes, and both of them have same mass
Yes.
and same charge,
Yes.
and let's say same spin as well. So from outside they look totally identical.
Okay.
But maybe one formed from one giant star and another formed from 10 stars, three planets,
Yes. Okay.
gas cloud. So, if there is no way of knowing regarding these entropy thing, or if entropy didn't exist inside them, then it would be impossible to know or to distinguish between those two.
Yes. Okay. So understood.
How do you basically distinguish both?
Okay. So that's the same question I asked Uday Jha. So I said that if a diamond falls into it, into a black hole, so would the Hawking radiation be the carbon atoms of that specific diamond? So he said it. I can't remember his answer, but uh, there's an information, like the arrangement of that information is lost. Like if we throw a diamond into the black hole, we'll get the Hawking radiation, but I don't know would it be the carbon atoms of that specific diamond, but we will get that matter back, but the arrangement would be different. So that seems a case of information loss for to me, but I may be wrong also. So
So the information uh, can be lost, as you said, but what about the entropy? Would that just add up,
yep,
or
yes,
or it, yeah, it would be adding up, right?
yes, and
And
like
those would be taking in form of Hawking radiation.
okay, so one more thing, that there's a law in thermodynamics. It says that when when two entropies of two systems combine, what would happen? That the specific the that the product system would have higher entropy than both of them. So like two black holes collided, their entropy, the product of those mergers would be that black hole would have greater entropy the than its parents, black holes. So that is the thing that I also didn't get it. So I think so. You got me right.
Yeah,
That
yeah. So if black hole A and B would combine, then it would be just a simple sum or even higher than A plus B.
it would be higher than a plus b. Uh, like didn't get it. The laws say that it should be higher.
No, but higher than what? Higher than A and B individually, that is obvious. But is it exactly A plus B or even higher than the sum of the individual
It's
passes?
higher than the sum of a plus b.
Okay, that's now not quite intuitive. But if the law says so, then there should be a breaking point inside all the black holes and all.
Yep, that's that. These were the questions that I asked to Uday Jha, who he was also like these are pretty hard questions, right?
Yeah, how are we supposed to know these questions?
Yes,
These are
just
all
make
yet
guesses.
hypothetical concepts. So either the black hole could have hypothetically infinite amount of storage, which doesn't make quite sense, but it might, as we just
Yep,
wonder or hypothesize the universe to be infinite. So could the storage house be? Maybe these are the storage house of universe. Who
yep.
knows?
The Yep, the thing that I've mentioned, like that information loss, the particles are not getting lost, but their arrangement is getting lost. So that arrangement of that specific diamond is not there with us now. There we only have the particles that made up them. So it's
What
like
do you exactly mean by the arrangement of things? Like, are we talking at the level of individual atoms or even lower
no,
than that?
like like
Okay,
speaking
so
like
let's imagine a diamond having a specific pattern of atoms, right? We're
yes,
talking at the atoms level. So when you say the information of that diamond is getting lost, do you mean the specific arrangement of
yep,
atoms inside, or even we're going lower than atoms?
yep, the arrangement of those, like the carbon atoms that they made up, they had a specific arrangement for that specific diamond that is just lost. Like uh, it's
Aren't those the same for every diamond?
yep. No, I don't think there are different combinations for different diamonds. They are not the same.
No, if we speak about a specific species, let's say 24 karat gold. So
Yep,
what I was assuming, though I'm not sure, but each and every 24 karat gold on Earth would be identical in the arrangement,
okay,
in how the atoms are arranged. Like if we see glucose, like
yep,
it's C6H12O6 arranged in a particular shape. So that is uniform in all across every glucose we will come across.
yep.
So
Like
what exactly gets lost if we somehow recreate another diamond? So we are basically recreating the entire structure of it. So
Yep.
what actually?
So like in that specific diamond I was talking, like there are six carbon atoms here, six carbon atoms lined here, and
Okay.
that is different in every diamond. Like they are not the exactly the same. So their combinations are different. Their carbon atoms are a little different. Their positions are different. They one can be arranged
Have
left.
you have you seen the structure of glucose?
No, I haven't.
What about benzene?
Okay, I do not haven't gone to that chemistry part.
It's the famous hexagon. You can just search it
Yep.
up real quick. It's just the
Okay,
hexagon.
I've heard about it, but didn't know that much.
You can just search it up in your screen right now very quickly. It's the famous hexagon-shaped chemical that we study, and it's same across every benzene.
Okay, no, like that was a particular combination. There are many different combinations in that specific atom, and they are lined left, up, right. So there are different combinations. Like it's like saying that each human being's uh, atoms are the same, are in the same combination. One there is one left, there is one right. It's not like that.
Also, you're saying treating each individual atom as individual personality and exactly preserving the exact position of
Yeah.
every atom.
Yes, that's lost.
Yeah, but what is the use of that if basically all the atoms have equal properties?
Okay, it's like if I put my chair into that black hole, it would be like uh, putting into a big mixer and mixing all it, and we get an carbon atom out of it. It comes rearranged. Okay, my phone died.
Okay.
So okay. So did you get me? What was I saying?
Yeah, yeah, yeah.
Okay. So
So
these
this
black holes.
Hawking radiation leakage, what was it as per you? Was it entropy or
Okay, so entropy, as I was saying, that the entropy in that black hole is not increasing. So to compensate for that, we are getting Hawking radiation. And another example that I used to think of is that whenever we think, we get in memory that uh, let
hold
me
on, hold on. The first assumption you made is the net entropy of a black hole isn't increasing.
yeah,
So it's a constant.
okay, it does not increase, so it's an constant. Yeah,
It doesn't increase or it has zero entropy and everything just whatever.
no, that's what I think. That's what I think. That's my opinion that it does not increase because it's in very tight space. The particles can't move, right?
Yeah,
So it should mean that there should be no entropy. The particles are not moving.
yeah, right,
So wouldn't that mean that there should be no entropy of a black hole?
right. But do they have it? I don't know.
Okay,
Do they have it?
uh, okay, so that was my thinking. So to compensate for that, there is Hawking radiation. So this is my view on those in these black holes.
No,
So
what does the physics say? I mean, do black holes have entropy?
yes, there's an equation for it. It's like the more it's related to the there's a famous equation. It's SB4, which something like that of Stephen Hawking's. It relates the entropy of a black hole to its event horizon, but I still did not get that.
Oh, okay. But yeah, you are right at the point that inside the black hole it is so compact that none of its particles should be moving. So it technically should have zero entropy.
Yeah. So uh, what I like to think of it is like the black hole uh, is making a deal with the universe that it would have zero entropy, but it would increase the entropy of the universe as a whole. So that's why it releases Hawking radiation. So this is my way of thinking that it releases Hawking radiation for like conserving the laws of the universe.
So of the entropy, whatever falls into it.
Yeah,
Yeah, right. So that logically that should be like if I put an entropy of A inside an object into a black hole, then the Hawking radiation out of it should exactly be A.
yeah. Like let's say that that particular object contain 10 atoms. So
Yeah, right.
for that Hawking radiation, it would be also 10 atoms. It will give that, like it's in a specific arrangement of an, let's say, of uh, of a square of a square, and it will not release that specific arrangement of that specific square, but it will
Yeah, but
release
just
it
10
half.
atoms.
Yeah.
Right. So is it your thinking or this is actually the case?
Okay, so that's my way of thinking, what I've learned and concluded from my learning. So
Oh, okay.
I think so that should be the case, that it releases all the specific atoms, but not the specific combination of that particular thing that followed.
Right.
Okay, so black holes are really complicated, and there's one more complicated thing. These are called naked singularities. People suspect that naked singularities are easier than black holes, but I don't see that happening. These naked singularities, for me, they should not exist because they are massive, and if they are massive, they should curve space-time, and around them there should be a curvature where the light cannot escape. Or what we can say is that uh, the particular singularity has lower mass than the black hole singularity, and its event horizon is very small to observe. So that's what I think of it, of naked singularities.
Is there any concept of the conservation of uh, this, what you said? Uh,
Entropy.
yeah, entropy.
Yep. With conservation of entropy, it always increases. There are thermodynamical laws to it. There's the second law, and there's many other laws which say that the when system A and B added together would be the product of the product would have bigger entropy than system A and B. So there are laws regarding it, entropy.
Okay, imagine this. I have a system, I have a system at space,
Yep.
and it is a system totally independent of any forces on it. And I have a free space to move, right? So,
Okay, can you repeat the last part? Your voice buffered and I couldn't get it.
okay. So, imagine I have a system and it is totally independent of any forces acting on it. And let's say we have five atoms in it, in the system, and we have plenty of space for them to move.
Yep.
Right. So now the system has some entropy in it, right? Now what I do is to decrease the boundaries of my system very slowly and eventually come to a point where those five atoms are stick so firmly to each other that they are not moving at all, right?
Okay.
So basically I make the entropy to zero
Yep.
in
But
my
that
system.
but that system, their combination of that combination of five would still be moving.
Um, no, why?
Because like this motion stuff, like it's not around in a black hole or something. It's in a box that that's isolated from the universe. It has five atoms, and if those atoms collided and form a molecule, that specific molecule would still move.
How about if they not form molecule?
Okay, so that would mean that there are more particles and more spaces, so the entropy should increase.
No, there are five individual atoms, and I make them come to a stage where motion is not possible. Like think of five
Hmm.
atoms as bottles, individual bottles, right?
Okay.
So what I did is to tie all the five of them so firmly that they are not moving across each other or in any type of motion. They are just tied up very firmly. So what I did is to make their entropy zero. What is the fault in it? Is there any problem?
Okay, I don't see any problem in it.
So what you just imagined is these five bottles forming an individual atom, sorry, an individual molecule and moving in within themselves.
Yeah. But what I imagined is that you said firmly, very firmly. So I thought that the molecule would not be moving.
Yeah, that could also be the case. If you imagine the case of the molecule, then also it isn't moving.
Okay,
So
but
technically we have zero entropy.
it seems like so, but I don't know how are you going to do that.
Well, basically, okay. So what makes all the particles as per your your speech, what made you think that the entropy, the overall entropy inside a black hole, an independent black hole on which we are throwing nothing, has an entropy of zero?
Okay, so the particles aren't moving, so that's why
And what is the reason for that? Why the particles are not moving?
the gravity is so intense that it forms in singularity,
Yeah,
and
exactly. And that is what I hypothesized in my system. So the basically the gravity would be so strong that the individual atoms won't be moving at all. They would form a rigid one structure,
okay,
of having five distinct atoms, but they are not in motion anymore. So they are, what I meant by firmly stitching it is basically that exact thing that you mentioned in the case of black hole.
yep. But
So
what's the case? What's the difference between that black hole and your system is that this black hole has energy, has more energy than your system, and to maintain the laws of the universe, it emits Hawking radiation.
Hawking radiation, that should be the conclusion part. That is where our talk should lead to, not like to treat it as a fundamental property of black hole. I just gave you the example of five particles coming close to each other to a point that they are not moving at all.
Yep.
So there was some entropy at the start, and what
Now,
we did is to bring the entropy to zero.
yep.
So where did the entropy go?
Uh, it.
As yeah,
I. That's what I also thought for the case of black holes, but I didn't imagine it this way. For the black holes, I just imagine uh, there's no movement, so no entropy increase, and that's why the black hole releases Hawking radiation. So, and more simple way that I imagined is that in our brains, what happens that whenever memory is created, the neurons are in a specific state, and the entropy decreases, and our brain releases heat to compensate for that. It's like an AC in a room. It's cooling this side down, but it's heating the other side up. So, so that is how the laws are getting
hold
conserved
on.
in
Why
this black hole
does the
system.
entropy decrease in this case?
What would be in your system entropy
No, no,
decrease?
no. The brain that you just explained.
The neurons, then the neurons combination. That's what I think.
Yeah, so the neurons combination make the entropy go overall down.
Yep.
And why is that?
They are in a specific state for that specific memory. They are in the ordered state for that memory. That's why.
Oh,
And
okay.
and our brain releases heat energy to compensate for that.
So this should be a spontaneous process. So our
Yep.
brain should always, from since the birth, it should be like it always is creating new memories, right?
Yep.
So it's constantly releasing heat and is constantly going to more stable. Sorry, not stable. The
Yep.
correct word is what organized, I guess.
Yep. Yes, our brain is always emitting heat.
Okay. So coming back to our system, so it in theory should release something in order to
Yep.
compensate to that earlier entropy, right?
Yes. It may give, like, I think so, an atom should be released or something like that to compensate for that. But I don't know how.
But it should release something in order to preserve the law.
Yep, that's where the Hawking radiation comes in, right? But in your system, it's pretty different from the black hole case.
Yeah.
I don't think so that system would be would be possible, physically possible. We can't be able to do that. It's okay. I think so. This
Because
system has no
yeah,
expectation.
if you speak independently, then if it of course wouldn't be possible because the mass itself wouldn't be enough large enough to get
Yep.
them to a state that they are not moving at all.
Okay, so your specific system, it's like us. Uh, it cannot be that specific case. It's an use. It's different from the black hole case, and it's in this black hole case, it releases Hawking radiation to compensate for that. But in your system, it cannot compensate, so it's breaking laws, and it should not be possible.
Right.
So it's so in this book I was just reading about this, and he was answering questions about what's the what was before Big Bang, and he said it's like asking what's south to south. It's meaningless. So this is that's I pres- uh, how I think of this system.
Right.
Okay, so I think so. We should get to the topic. We are at our last summary of star formation process. Star formation begins with the gravitational collapse of molecular clouds. Protostars evolve through different classes, shedding their outer materials. Once nuclear fusion starts, stars enter the main sequence phase. Yes, one more question was there. You said that what is sub-millimeter emissions? So, like, it's a continuous spectrum of that radiation that we have been receiving from that star. So, that is the sub-millimeter emissions. So, ladies and gentlemen, do you have any questions? Okay, I don't. You wanted to say something, Saksham, and
No, no, we're good.
okay. So, I think so. We have gone over time, 35 minutes over time. So, I think so. We should end the presentation. So, thank you everyone for joining us. So if you have any questions, you can ask us.
Okay, thank you.
Thank you.